Hi class, welcome back to thermodynamics. And so this is going to be our final lecture of new material in thermodynamics. I posted the exam format and some review questions for the final. So definitely go through those on Moodle. There's also the answers and some selected solutions posted, and send me an email or post to the forum if you have any further questions about any of that. So we're going to finish up this course by looking at the air standard cycles. So we use these when we're dealing with engines. So as you've seen, hopefully in the other videos that you watched about different engines, there's the spark ignition engine and there's also a compression ignition. So in order to model spark ignition, we use the Otto cycle. And with the Otto cycle, we have our four processes. So process 1 to 2 here is isentropic compression of air as the piston moves from the bottom dead to top dead center. And process 2 to 3 is constant volume heat transfer to the air from an external source while the piston is at top dead center. So this is the ignition of the fuel-air mixture and rapid burning. And remember here, we're modeling air as an ideal gas. And remember, isentropic tells us that this is internally reversible. So we have constant entropy. So delta S is 0. And for process 3 to 4, we have isentropic expansion, so that's known as the power stroke. For process 4 to 1, we have a constant volume process where heat is rejected from the air while the piston is at bottom dead center. Okay, so both process 2 to 3 and 4 to 1 in the Otto cycle are constant volume. So the diesel cycle, so these would be vehicles that require diesel gas, is a compression ignition system. And so for these are very similar processes to the Otto cycle, except that for 2 to 3, process 2 to 3, we have constant pressure heat transfer rather than constant volume heat transfer. That is the major difference, one of the major differences. And the second video you watched for this week compared and contrasted the two cycles and the differences in the ignition systems. And lastly, today we're going to look at the Brayton cycle, which we use for gas turbines, modeling gas turbines. So this is another air standard cycle, so you modeling air as an ideal gas. And for this process for process 1 to 2, we're going through a compressor, so we're putting power into our system, and that would be an isentropic process. So once again, constant entropy. So for process 2 to 3, we're going through a heat exchanger where heat is going in at constant pressure. For process 3 to 4, we have a turbine where we're getting power out of our system, another isentropic process. And then finally, for 4 to 1, we're going through another heat exchanger where we get heat out. So that's Q dot out, and that is at constant pressure. So the major differences here, for the most part with these cycles, we're dealing with piston cylinder assemblies. For the Brayton cycle, we're dealing with compressors and turbines. All right, so let's get started and jump right into an example problem dealing with the Otto cycle. So this is number 9.3 from your textbook. And so at the beginning of the compression process of an air standard Otto cycle, P1 is 1 bar, T1 is 290 Kelvin, and V1 is 400 cubic centimeters. The maximum temperature in the cycle is 2200 K, and the compression ratio is 8. So we're going to have to determine the heat addition in kilojoules, the net work in kilojoules, the thermal efficiency, and finally, D, the mean effective pressure in bar. Okay, so let's draw our process first on a TS, and then we're going to look at it on a PV diagram. So we're going to look at the Otto cycle. Okay, so this is going to be our TS diagram and, whoa, TS diagram. And over here, we're going to have our PV diagram. And remember, we're using air, which is an ideal gas. So I'm going to draw a little teeny tiny vapor dome in the corner to show that we're far off to the right of the vapor dome, to the upper right. And so looking at this, we are going to start at P1 is 1 bar. So we're going to start state 1. And if we go back for a sec, we see we have isentropic compression. So isentropic compression, we're going to get an increase in temperature and entropy is constant. So this would be 1 to 2. So over here, let's put 1 over here. And with isentropic compression, we're getting a decrease in volume and an increase in pressure. So we'll end up probably somewhere over here. So there's process 1 to 2 on the PV diagram. And so then for process 2 to 3, let me just flip back here. We have constant volume heat transfer to the air from an external source while the piston is at top dead center. And so in this case, we're going to have an increase in temperature and we get an increase in entropy. So this is 3. And then 2 to 3 here, we're going to have constant volume and we get another increase in pressure as we are increasing temperature. Heat in. All right. And then next, so then 3 to 4, we have isentropic expansion. So for isentropic expansion, we're going to once again have constant entropy and we're expanding, so we're going to be cooling. Oops. Okay, so that's 3 to 4. And so over here, we're going to get a drop in pressure with cooling. And we're going to be expanding our volume. Okay, so this is 4. And so 4 to 1, we're going to have constant volume where heat is rejected from the air. So we'll get cooling. All right, so here we're getting a decrease in temperature and in entropy. And then over here, we're going to have constant volume and a decrease in pressure, so decreasing temperature. All right, so there's our TS and PV diagram for the Otto cycle. And so we want to find the heat addition. And let me just write our find. So we want to find Q in. We want to find net work, which is going to be W cycle. We want to find the thermal efficiency, which is going to be eta. And we want to find the mean effective pressure, which is the ratio between W cycle and the amount of volume displaced. So the volume change in process 1 to 2. Okay, in our first compression process. Okay, so to solve this, let's first start by fixing our states. So we know it's state 1 that if we look at A22, so A22 is our table for air, ideal gas information, one of them. So from table A1, for a temperature of 290 K, we can look up, so this is table A22, for 290K, we can find that U1, I'm not going to do all the interpolation out anymore. U1 is 206.91 kilojoules per kilogram. And we're using U now of the internal energy because we're dealing with a piston cylinder. We're not dealing with mass flows through a turbine. So we have a piston cylinder here. So we have U1. And so also another thing that we can look up in our tables here, let me open up my table and look at A22. And you see these P sub R's and V sub R's. So these are pressures and volumes entirely as a function of temperature. And so when you look at the ratio, say, of P, of like, say, V, if you look at the ratio, say, V1 to V2, it'd be the same as the ratio of VR1 to VR2. Okay, so we can use these comparative ratios to actually determine the pressures and volumes. So here we're given the compression ratio is 8. So for 2, we're given that the compression ratio is 8. And the compression ratio is defined as V1 over V2. Okay, and it's going to be the same as VR1 over VR2. And so we can solve for VR2. And that's going to be VR1 over R. And so here we can look up VR1 in the table. And we get that that is 676.1. Okay, and so this is, so there are no units on this, okay? Because it's meant to be used in these ratios. Now, we use 676.1, and we divide by R, which is given to us as 8. And that gives us a VR2 of 84.51. So then going back to the table, you can interpolate and you can find that T2 is 652.4 Kelvin. And then you can further from that find that U2 is 475.11 kilojoules per kilogram. All right, so I'm going to move over here for state 3. So for state 3, we have the maximum temperature in the cycle is 2200 K, and we get the maximum temperature at state 3. So T3 is 2200 K, right? Because that happens after the heat addition to the air. And so from that, we can go to the table and we can find that U3 is 1872.4 kilojoules per kilogram. And we can find VR3 is 2.012. Now finally, looking at state 4, we have that, once again, so here we have VR4, because we're dealing with isentropic, an isentropic process, is going to be, so VR4 over VR3 is going to be the same ratio as V1 over V2 or VR1 over V2. And so it's going to be equal to VR3 over times VR1 over VR2, or which is the same as just if we said V1 over V2, which I'll write it that way. And this is going to give us 16.096. Okay. All right, so, and that's going to be the same as, we could have also found that doing R times VR3, right? Since V1 over V2 is the same as VR1 over VR2, which is the same as R, which is 8. All right, and so from that, we can get the temperature, and I'm going to add another sheet for that. Okay, so this is still state 4. And so we can get that T4 is 1159.3K after interpolation. And we can also get that U4 is 897.3 kilojoules per kilogram. All right, so now A, we were looking for Q23. You're looking for Qn, which is Q23. And so we were also given that V1, well, let's just write this out first. So this is going to be M times U3 minus U2. And so something that we were given earlier is we were given V1. And from V1, we can compare, we know that V1 is equal to M times the specific volume. So we can go ahead and we can solve for M, and we get that M is equal to 4.806 times 10 to the minus 4 kilograms. So just make sure to convert cubic centimeters to cubic meters in order to do this. And when you plug in the U's that we found, U3 was 1872.4, U2 was 475.11, you get that Qn is going to be 0.6715 kilojoules. For B, we have W cycle, which is going to be Q23 minus Q41. And so we already found Q23. So it's going to be Q23 minus the M that we found times U4 minus U1. And U4 we looked up and interpolated and found was 897.3. U1 we found was 206.91, and so we get a W cycle of 0.3397 kilojoules. For C, we have eta, our efficiency, is equal to W cycle over Q23, W cycle over heat in. And so it's just going to be B over A, which is going to be 0.3397 over 0.6715, and the units will cancel out. And that gives us 0.506, which is the same as 50.6%. Okay, and then lastly, we can get the mean effective pressure. And we want that in bar. Okay. So here we get the mean effective pressure is going to be W cycle, which is 0.3397 kilojoules, divided by V1 minus V2, which is going to be the same as V1 minus V1 over R. So we can use that volume that was given to us above. And we get that we get 0.3397 kilojoules per kilogram divided by ultimately 350 centimeters cubed when we do this, and we have to convert. So remember, there's 100 centimeters cubed, so cube that whole thing in a cubic meter. So to divide by that, and we get 971 kilopascals, which is going to be 9.71 bar. All right, so we have quite a bit more to get through today, so we're going to keep on going. So for this next one, we're looking at the diesel cycle. And for this, it says the pressure and temperature at the beginning of compression of an air standard diesel cycle are 95 kilopascals and 300 Kelvin respectively. So at the beginning, that's going to be our info for state 1. So that's going to be P1 is 95 kilopascals and T1 is 300 Kelvin. And so let's start drawing this as we go. So I'm just going to draw this one on a PV diagram. Remember, we're dealing with air as an ideal gas, so I'll draw a teeny tiny vapor dome. And so for 1, we're over here. All right, and so we have compression, so we're going to get a decrease in volume and an increase in pressure. So let's go over here. So this is 1 to 2. And at the end of the heat addition, so heat addition, just like with our Otto cycle, takes place in process 2 to 3. So at the end of heat addition, that's going to be state 3. We have P3 is 7.2 megapascals, and T3 is 2150 Kelvin. So then we want to determine the compression ratio, the cutoff ratio, the thermal efficiency of the cycle, and the mean effective pressure. So now for the diesel cycle, we're going to have a constant pressure process from 2 to 3. All right, so we know that P3 is equal to P2. So this is also equal to P2. And then we're going to have an increase in volume from 3 to 4 with expansion. These should be much nicer looking curves here. It's kind of hard to draw on this. And then we're going to have constant volume from 4 to 1. Okay. So remember, different from our Otto cycle, we also have a constant pressure process in here. All right. So now we want to find the compression ratio. So that's our R. So we can get that from V1 over V2. We can get the cutoff ratio is defined as V3 over V2. All right, so where we have this constant pressure process. And that's going to be the same as T3 over T2 is another way we can find that. We know what thermal efficiency is, and we know what mean effective pressure is. So let's go ahead and continue fixing our states. So I'm just going to keep writing info for 1 down here. And so at 300 Kelvin and 95 kilopascals, we can go to table A22 as we were using in the last problem, and we can get U1 is 214.07 kilojoules per kilogram. And we can get VR1 is 621.2 and PR1 is 1.3860. All right, and so then, oh no, sorry, I'm distracted by the battle that might happen behind me. Put it in the shot if you want some entertainment. Okay. So then, okay. So for state 2, we have isentropic compression happening. So because we have isentropic compression, we know that PR2 is equal to PR1, which is times P2 over P1. All right, since it's going to be the same ratio, that same compression ratio, R. Sorry about that. Same compression ratio, R. And so there we get that we take our PR1, which is going to be 1.3860 times P2 over P1, which is going to be our 7,200 over 95. And that's going to be 105.04. All right, and then next we can look up, well, we can interpolate to get T2 from table 822, and we get 979.6 Kelvin. And VR2, using interpolation, is going to be 26.793. And we can also find H2, and that's going to be 1022.82 kilojoules per kilogram. Okay, so the thing is, so in the first problem, we were dealing with, so if we look at our model for the Otto cycle, we are dealing with these constant volume processes occurring in a piston cylinder. And remember, work is P delta V. And for constant volume, we use internal energy, U. But remember, enthalpy is U plus PV. And so for the diesel cycle, what happens is when we have this constant pressure process going on in 3 to 2 or 2 to 3, we actually need to look up the enthalpies. Okay, so U plus PV, okay, because we do have a delta V. So for 4-1, so for state 1 and state 4, we look up U, because that would be the same thing like our piston cylinder at constant volume like we did with the Otto cycle. So that's why I looked up H instead of U. Let's add a page. All right. So then for state 3, we have T3 is 2150K. We were given that. P3 is 7,200 kilopascals. And so we can find H3 in the table, which is going to be 2440.3 kilojoules per kilogram. And we can find VR3 in the table, and that is 2.175. So for state 4, we have isentropic expansion. And so with this, we have VR4 over V3. So this ratio of the volume differences so for state 4 over state 3 is going to be the same ratio as if we did V1 over V2 times V2 over V3. So basically here we're saying that V4 over V3 is going to be the same as V1 over V3. And so this is going to be the same as V1 over V2. And V2 over V3, that ratio is the same as T2 over T3, using the ideal gas law. And so then V1 over V2, we know that because we have VR1 over VR2, and that's going to be times T2 over T3. And so this is going to be 621.2 over 26.793 times 979.6 Kelvin over 2150, which is going to give us 10.56. And so from there, we can find that VR4 is going to be V4 over V3 times VR3. So we can find our VR4, and that's going to be 22.98. And so from that, knowing the VR4, we can interpolate to find T4 in A22, which is going to be 1031 Kelvin. And then lastly, U4 is going to be 785.75 kilojoule per kilogram. All right, so now we can just go ahead and finish off what we were actually looking for in this problem. Now that we fixed all our states, it's always the first place you should start. And so our compression ratio, R, is going to be V1 over V2, which is the same as VR1 over VR2, which we already know is going to be 621.2 over 26.793. And that is going to give us 23.19. So RC, our cutoff ratio, is going to be V3 over V2, which is going to be the same as T3 over T2. All right, so that's for that constant pressure process. Okay, so end over beginning. And so that's going to be 2150 over 979.6. So basically the reciprocal of that. And so it's going to be 2.19. Almost there. Okay, so for the next one, C, we're looking for the efficiency. So eta is going to be W cycle divided by Q23. So for this, since we don't have the mass, or we weren't given a total volume or anything where we could find the mass, so I'm just using the specific, so work on the W cycle on a mass basis over Q on a mass basis. So this is going to be equal to H3 minus H2. All right, so that's for the constant pressure process, minus U4 minus U1, and that's for the constant volume process, divided by Qin, which is H3 minus H2. And this will give us 0.597, which is 59.7%. For D, we have the mean effective pressure is going to be W cycle over the displacement, which is going to be V1 minus V2 for compression. And so this is the same as W cycle over V1, and I'm just going to pull out the V, so that's 1 minus V2 over V1. And so we need to find V1, and we can find V1 using the ideal gas law, which is going to be RT1 over P1. And so it's going to be 0.287 kilojoules per kilogram Kelvin times T1, which is 300 Kelvin, divided by P1, which was 95 kilopascals. And so V1 is going to be 0.9063 meters cubed per kilogram. All right, and so now we can just plug that in. So MEP is going to equal our W cycle, which is going to be 845.8 kilojoules per kilogram. And that's just this numerator up here. Let's see, divided by V, which was going to be 0.9063 meters cubed per kilogram times 1 minus V2 over V1, which is going to be the reciprocal of R. So it's going to be 1 over 23.19. So we found this in part A. And this is going to give us 975 kilopascals. Okay, so that gives us some information on, it's a kind of another sort of efficiency or performance metric. It's a performance metric for the engine. All right, so it's the amount of volume, the average volume per, the average pressure per volume displaced in compression. All right, so now we're gonna redo the same problem, so same exact conditions as before. I'm not gonna redraw out the scenario or anything, but here we are doing the cold air standard diesel cycle. And so the key here is when you see cold air standard, this tells us we can assume constant specific heat capacity at our low temperature. And so our low temperature here is going to be 300 K. So assume C equals constant specific heat at 300 K for the whole cycle. So that's that assumption. All right, and so then we could go into our table and we can go to table A20 now. And we can look up K for a temperature of 300. And so here, K is equal to 1.4. Okay, so then rather than using the ratios, the like VRs and PRs, to find the compression ratio and the cutoff ratio in the tables, so you don't have to go to A22 to do that. You can do it using K, and I'm going to show you how to do that here. All right, so for the most part, a lot of our information is going to be similar, except for some stuff starting at state 2 is going to be different. So we can find T2 is going to be P2 over P1 times to the power of K minus 1 over K times T1, which I'm just writing over there. And so this is going to be equal to, ultimately, if we plug in K, we plug in our pressures, we get 1033.1 K. All right, so then for 4, we can get V4 over V3 is going to be V3 over V4. And if you want to review this stuff, it's summarized in handout number 5. That's posted under handouts on Moodle. And this is for our isentropic processes. and that's going to be K minus 1 times T3. And I feel like I need to rewrite this. That's a 3, that's a 1. And that'll give us 837 Kelvin. All right, so now for part A, our ratio is going to be V1 over V2, which is going to be the same as T2 over T1 to 1 over K minus 1. And that's going to give us 22.01. All right, so that is a decrease in ratio compared to the first problem. All right, so for B, we're looking for RC, and that's going to be V3 over V2, which is the same as T3 over T2, which is going to be 2.081. So that's another decrease compared to our last problem, 920. C, eta, is going to now be, you can find as CP, T3 minus T2. So here we looked up, where did it go? Here we looked up enthalpies in A22, but if you assume constant specific volume, or constant specific heats, you can do Cp delta T to get enthalpy. And remember, CV delta T is in specific internal energy. And so, and then we are going to divide by Cp T3 minus T2. And you could look up CV for a temperature of 300 Kelvin in A20, and you get 0.718 kilojoules per kilogram Kelvin. You can look up CP, and that's going to be 1.005 kilojoules per kilogram Kelvin. And so our efficiency is going to be 0.657 or 65.7%. So that is a big increase in efficiency compared to the last problem when we weren't using the cold air standard assumption. And then MEP is going to be still W cycle over V1 times 1 minus V2 over V1. And so here, V1 is still going to be RT1 over P1, which we found here, which is 0.9063. So then when we plug everything in, so remember W cycle is going to be the numerator of part C. And so MEP is going to be 763.9 kilojoules per kilogram. And we get 0.9063 meters cubed per kilogram times 1 minus 1 over part A. We got R is 22.01. And this is going to give us 883 kilopascals. And so this is also up compared to our last problem where we didn't have the cold air standard assumption. So when you assume constant specific heats for the whole process, you end up overestimating your efficiency and also your MEP, and underestimating your cutoff ratio and your compression ratio. So that's just something to keep in mind. But you could, so this would just be the cold air assumption. So if you're ever told to do the cold air standard assumption, you use constant specific heats at the lowest temperature of the cycle. All right, let's look at one more together. And now we're looking at the Brayton cycle. All right, and so here we're dealing with turbines. And so here we're dealing with control volumes once again. So we're looking at volumetric flows. So we have our little dots, everything over our W's and over our Q's and over our M's. And everything then is going to be in terms of watts. So energy per time or power. So an ideal air standard Brayton cycle operates at steady state, it operates at steady state and produces 10 megawatts of power. There's some grammar issues in that sentence. Operating data at principal states in the cycle are given below. We're going to sketch the TS diagram for the cycle to determine A, the mass flow rate of air in kilograms per second. So we're looking for M dot. The rate of heat transfer in kilowatts in the working fluid passing through the heat exchanger. Q dot in. And the thermal efficiency, so that would be eta. Okay, so now let's give this a sketch. So we have our compressor. I'll make purple. Wow. So we have our compressor, and I ran out of room, so I'm going to do it like this. We have W dot C, so this is work going in. And so this would be 1 and 2. And then we're going into a heat exchanger where we have heat going in. All right, and so that's 2 to 3. And so then we're going into a turbine where we're getting power out. That's going to be 3 to 4. Where we're going into another heat exchanger where we have Q out. And that's going to be 4 back to 1. All right, so there's our little diagram of what's going on for the Brayton cycle. And then I'm also going to sketch our TS diagram. And once again, tiny vapor dome. Since we're dealing with an ideal gas, we're dealing with air. And so for 1, let's start here. We have compression, so we get increase in temperature. And then for 2 to 3, we're going to increase temperature because we have heat going in. Increasing entropy. And so this is an isentropic process first from 1 to 2. So when we're going through the compressor, it's isentropic, so delta S is 0. Same thing when we're going through the turbine, it's isentropic, so delta S is 0. And so then finally, oops. We are going back through heat exchanger and we get a decrease in temperature with Q out. All right, so we're given our information. You don't have really anything to look up here. So that makes this nice and simple. So for part A, W dot cycle is going to equal W dot for the turbine plus W dot for the compressor. And so this is going to equal M dot And so for the turbine, that's going to be 3 to 4. So it's going to be H3 minus H4. Okay, so we're positive for the turbine, minus or plus, then the compressor is going to be H1 minus H2. All right, so that's our compressor. And we can go ahead. We know W cycle is going to be 10 megawatts. So M dot is going to equal W dot cycle divided by H3 minus H4 plus H1 minus H2, which is going to give us 21.54 kilograms per second. All right, and so for B, we're looking for Q in, and that's going to equal Q dot 23, which is going to be M dot times H3 minus H2, which is going to give us 0.48. Oh, just kidding, looking at the wrong line. Which is going to give us 20.78 megawatts. And then lastly, C, our efficiency, is going to be W dot cycle over Q in, which is just going to be 10 megawatts divided by 20.78, which is going to be 0.481, which is 48.1%. All right. So that is it for new material. You have 3 problems for the homework, dealing with these, working with these new cycles, and definitely get in touch with me if you have any questions. And the final exam will be due Wednesday, May 13th by midnight, before midnight, and I'll let you know as soon as that is available. All right. Take care and have an excellent summer.